Hello learners, and welcome to a video tutorial over Atwood's machines. Now I've got three examples here. Pretty much it's just a system where you have two masses connected by a pulley, and they'll either be an acceleration one way or the other, or they might be a system in equilibrium. So here we have two masses just hanging over a single pulley. Here we have two masses connected through a pulley, but one's on an inclined plane. Here we have two masses, pulley again, but now one is on a flat plane. Or you could even have two masses on two angled planes connected by a pulley. All of these would be an example of an Atwood's machine. Now, we're not going to run through each example specifically, but what I'm going to do is show you an easier way to work a free body diagram for an Atwood's, and this can apply to any one. So let's start with this earring example of an Atwood's machine. So we just have our pulley and connected to a mass. Let's put a mass M over here, and then let's put another mass of 2M on this side. Now, if this is a frictionless pulley, then clearly, just intuitively you know, oh, this one's heavier, so it's going to drag it down. So there will be a net force in this direction for this mass. But there's a net force in this direction up for this mass. So how do we go about figuring that net force? Well, we can start by drawing a free body diagram for each mass. So I'm going to draw this, and we'll label this, let's do block 1 and block 2. So here's weight, Fg, and it would just be mg, and that's Fg2 for block 2. This block's weight, Fg1, would be 2mg. Now, both blocks have a tension force directed up. And those two tension forces are equal to each other. Now, you'd think, oh, they're both going up, so I'm going to add them together. Well, I'm going to show you how to redraw an Atwood's, and it's oftentimes helpful to redraw the Atwood's without the pulley. So what I'm going to do is I'm going to take these blocks and I'm going to swing them up, keeping all the forces the same, but swing them up so that there is no pulley. So, here we go. Let's draw our 2M block on this side, 2M connected through a string to my M block. Now both had weights going down, but remember I swung them up, so now my weights are going to the right and to the left. So this direction is Fg2, and then this direction is Fg1. Now their tension forces were both directed up, but now that I've swung them out, they're both directed in towards the center. So I've got Ft and then Ft. Well, now let's apply Newton's second law and look at the acceleration for the system, because both of these blocks are going to move together. They're going to have the same acceleration. So if I say the sum of all my forces is my mass times my acceleration. Well, the sum of my forces, the tensions are equal in magnitude and they're pointed at each other, which means they cancel out. So I would have Fg2 to the right and Fg1 to the left. Well, if I say Fg2 is mg, well then the right, let's just make the right positive. Well then the left, that would be minus 2mg equals ma. Well, mg minus 2mg is negative mg equals ma. Well, cross out, and I'm left with, oh, wait a minute, my mass would be the mass of the system. So that would be 2m plus m, or 3ma. So again, negative mg equals 3ma, cancel my masses, and I'm left with an acceleration that is a third of gravity. Which makes sense, because if I just had this block fall, well, its acceleration would be g. But it can't fall like that because it's got to pull this block up. So we get an acceleration of 1/3 of gravity, which means this block is accelerating negative g over 3 down, and this block is accelerating g over 3 up. Now we can apply Newton's second law to an individual block to figure out the tension. Let me redraw one more Atwoods for you, and let's do one like this. So I've got my pulley connected to my mass, connected to some other mass, and let's say that this one is m and this one is 2m, and let's give ourselves an angle theta here. Well, if I redraw this without the pulley, the forces that I have are my weight coming down, normal force coming out perpendicular, tension, tension, and then weight here. Well, redrawing this without the pulley, here's the 2m block, and here's the m block. Well, tensions are coming at each other. This block's weight is coming out like this, and those are the only two forces acting on the smaller block. Now, tension and normal force are perpendicular to each other, so I'm going to draw them just like that. But remember, look at weight. It's coming off at an angle, and it's coming off at an angle theta relative to the vertical. That would be how you could redraw this Atwoods. Knowing that your normal force is going to be canceled by your y component of your weight, you could figure out whether this would slide up or slide down based on what this FGX is. The two tension forces still cancel. So you'd have FGX of the larger block and FG of the smaller block. Depending on what angle it is, that would determine how it moves. So check out this little Atwoods that I've made here. So we have an Atwoods here, and I've got your rubber sled that you've worked with right here. And then I have, it looks like about, let's see, 50, 20. So I've got 70 grams on the other side. And right now, everything is in equilibrium. But if I add 10 grams to this block, here we go. This is difficult. Very carefully, the whole system gets out of whack. So my equilibrium